The Pythagorean theorem is a formula for right triangles saying that the sum of the squares of the legs equals the hypotenuse length. So that's commonly known as a squared plus b squared equals c squared. So the Pythagorean triples are any triples of integers that satisfy the Pythagorean theorem. So they would be examples of right triangles with all integer side lengths. So I really recommend that you have lots of the Pythagorean triples memorized because it's going to help a lot with speed and noticing patterns that other mathletes might not pay attention to. So there are lots of Pythagorean triples, but these are the 9 that I think are the most helpful and that are the most common in competition math. So you might be familiar with like 3, 4, 5, 5, 12, 13, 8, 15, 17, but I'd recommend even learning some of the more obscure ones like 11, 60, 61, 20, 21, 29, because it's going to make it a lot faster when those examples do show up in problems. So this first problem is pretty simple. So the question is, right triangle ABC has legs of length 3, 3, 3, and 4, 4, 4. Find the hypotenuse of ABC. So if we draw a picture just to get an idea what the problem's asking, we see that the legs are 3, 3, 3, and 4, 4, 4. And we can observe pretty easily that this is a scaled up version of a 3, 4, 5 right triangle. So we can see that the triangle in the problem is scaled up by a factor of 1, 1, 1. So that would make the hypotenuse of ABC 5, 5, 5. So 5, 5, 5 is our final answer. Okay, the next question is, find the area of a triangle with sides 13, 14, and 15. So when a lot of people see this question, their initial instinct is to say that the area is 13 times 14 divided by 2, which is 91. But the reason that's not the right answer is because this triangle is not a right triangle, because we can see that 13 squared plus 14 squared does not equal 15 squared. So let's draw a picture to get a better idea of what we're working with. So if we draw the triangle, we have 13, 15, and 14. And because we have the Pythagorean triples fresh in our mind, we might be able to observe a pattern using the Pythagorean triples. So we can see that we have the number 13. And if you go back and look at the slide with all of the examples of the Pythagorean triples, we can see that there's one that's 5, 12, 13. So to find the area of a triangle, we would need the base and the height. But because we don't have a right angle in the triangle, we're going to have to draw our own height or altitude. So if we draw the height, which is perpendicular to the base, then we see that we actually have 2 separate right triangles. So one with hypotenuse 13 and one with hypotenuse 15. So if we start with the one with hypotenuse 13, we can see that that's actually a 5, 12, 13. So 5 and 12. And now we can solve for the second right triangle, which is a scaled up 3, 4, 5, making this side 9. And we can see that 5 plus 9 do in fact add up to 14 for the base. So our answer would be 1/2 base times height, which is 1/2 times 14 times 12, which is 84. So some people may be confused on how we decided to put the 12 for the altitude instead of 5, but 13, 14, 15 triangles are really common in competition math. So when that shows up, they are expecting you to be able to recognize that 12 is automatically the height. So I would recommend that you just have that memorized. Anytime a triangle shows up with sides 13, 14, and 15, try drawing it in this way with an altitude of 12 and split it up into 2 separate right triangles. So the next question is, in the non-convex quadrilateral ABCD shown below, angle BCD is a right angle. AB equals 12, BC equals 4, CD equals 3, and AD equals 13. What is the area of quadrilateral ABCD? So whenever we have a geometry problem with a picture, the first thing we want to do is label everything that's given to us. So we see that AB equals 12, BC equals 4, CD equals 3, and AD equals 13, and angle BCD is a right angle. So at first, this quadrilateral looks really funky shaped, and we don't have a set formula to solve for the area like we would a square or a triangle, but we see that BCD is a right angle, and BC is 4 and CD is 3. So that should make us think of a 3, 4, 5 triangle. So if we draw D to B, we've actually formed a 3, 4, 5 right triangle with BD is 5. Now we can see that we formed a larger right triangle, 5, 12, 13. So because we want to find this area, we can find the area of the whole triangle and subtract the smaller triangle, which would get us the area of quadrilateral ABCD. So to find the area of the whole triangle, we do 1/2 base times height, which is 1/2 times 5 times 12, which is equal to 30. And then the area of triangle BCD is 1/2 times 3 times 4, which is equal to 6. So to find the area of quadrilateral ABCD, we would do 30 minus 6, which equals 24, which is our final answer. Okay, next question. Quadrilateral ABCD is a trapezoid. AD equals 15, AB equals 50, BC equals 20, and the altitude is 12. What is the area of the trapezoid? So we should have the area of the trapezoid formula memorized, but if you don't know it, it is 1/2 times B1 plus B2 times height. So based off of the picture, we have B1. We don't have B2, but they did give us that the height was 12. So to find the area of the trapezoid, we would have to find B2, which is this length. So they gave us the altitude was 12, but the way they drew it was in the center of the trapezoid, but that doesn't give us much to solving the length of CD. But if we draw altitudes down from A and from B, and these are still length 12, we can see that we've actually formed two separate right triangles. So we have a 15, 12, 9 triangle, which is a scaled up 3, 4, 5. And then we also have a 20, 12, 16 triangle, which is also a scaled up 3, 4, 5. And we can see that AB is equal to this length, which would make B2 equal to 9 plus 50 plus 16, which is 75. So in that case, B2 is equal to 75. So if we plug that into our equation to solve for the area, we get that the final answer is 750. So we can see how knowing our Pythagorean triples just saved us a lot of time in solving this question. Okay, this question is from the AMC, which is one of the most prestigious math competitions that many high schoolers don't even get the opportunity to take, but knowing the Pythagorean theorem actually makes this question a lot more manageable. So normally they don't give you the picture, but because the AMC problems are more complex, we provided the picture for you. So in quadrilateral ABCD, angle B is a right angle. Diagonal AC is perpendicular to CD. AB is equal to 18, BC is 21, CD is 14. Find the perimeter of ABCD. So as I said, whenever they give us a picture for a geometry problem, we first want to label what they give us. So we have that AB is equal to 18, BC is 21, and CD is 14. So we can actually use the Pythagorean theorem here to find the perimeter of ABCD. So to find the perimeter, we have to sum all of the sides of the quadrilateral. Right now, we have 3 of the sides, but we're missing the length of AD. So we can label that as X. So we see that we have 2 separate right triangles, triangle ABC and triangle ACD. So we can do the Pythagorean theorem twice. So first we want to find length AC. So AC squared is equal to AB squared plus BC squared, which is equal to 18 squared plus 21 squared. So I would recommend having your squares memorized up until 30 squared, because it's going to save you a lot more time in things like countdown round and sprint round, especially when you don't have a calculator. If you don't know your squares yet, then using a calculator is fine for now. But multiplying out your squares is going to take a lot more time, and other people might have their squares memorized, which means that they'll solve the question faster than you. So 18 squared is 324, and 21 squared is 441. And if you sum that together, you get 765 as AC squared. So we need to then find AD, and some people may square root AC squared to find AC, but to make this faster, we realize that we don't actually have to square root AC squared, because we want to find AD, and AD squared is equal to AC squared plus CD squared, which is equal to 765 plus 14 squared, which is 196, and this is equal to 961. And if you do know your squares, then you can recognize that this is 31 squared, which would make X equal to 31. So now we have that AD is 31, but your final answer is not 31. You have to remember that they're asking you to find the perimeter of ABCD. So you would have to sum 18 plus 21 plus 14 plus 31, which is equal to 84. So 84 is your final answer. Okay, so this is question 25 from a somewhat recent AMC8, which means it's going to be a lot harder than some of the easier questions, but it's a fun challenge problem, and knowing your Pythagorean triples really helps in solving it. A semicircle is inscribed in an isosceles triangle with base 16 and height 15, so that the diameter of the semicircle is contained in the base of the triangle as shown. What is the radius of the semicircle? So the first thing we want to do is label our drawing. So we have that the height is 15 and that the base is 16. So when we have an isosceles triangle, the altitude is going to split the base in 2 equal sections. So that would make both of these 8. Now we can see we have an 8, 15, 17 triangle, which is one of our Pythagorean triples. So we want to find the radius of the semicircle. So we have to figure out where to draw our radius in a place that would help us best solve the problem. So if we draw a radius here, perpendicular to the hypotenuse, we've actually made more right triangles. So if we label our radius R, and that's what we have to solve for. So we have to figure out a way to solve for R. We know that we can write the area of this larger triangle as 1/2 base times height, which is 1/2 times 15 times 8. There's also another way to write the area of the same triangle using a different number as the base. So in this example, 8 is the base. But if you imagine that the triangle was rotated, we can see that we have 17 as a base with R as the height. So in that case, the area of the triangle would be 1/2 times height times the base, which is 17r over 2. And these two quantities are actually equal because they both represent the area of the same triangle. So we can set 17r over 2 equal to 1/2 times 15 times 8. Cancel out the 2's, and we get r equals 120 over 17. And that's our final answer. Okay, this problem is a lot more tricky because it's number 7 on a Mathcounts target, which means you are allowed a calculator because you're going to be dealing with a lot bigger numbers. So right triangle DEF with sides of integer length has a perimeter of 40 meters. Semicircles are drawn with diameter DE and diameter EF as shown. If arc DEF is a semicircle, what is the total area of the shaded regions? So at first it seems like they don't give us the side lengths of the triangle, but they give us the perimeter, which is 40 meters. But because we know that all of the sides are integers, we know that it has to be one of our Pythagorean triples. So if you look back at the Pythagorean triples, you want to find one that has perimeter of 40. And if you sum them up, you realize that an 8, 15, 17 triangle has perimeter 40, which means DE is 8, EF is 15, and DF is 17. So they want us to find the total area of the shaded regions, which are parts of the semicircle. So what that means is we want to find the area of semicircle DE, but we want to subtract this region, and we want to find the area of semicircle EF, but subtract this region. So at first it seems like we don't have a way to find this pink and red region because it's not a semicircle and it's a shape we don't have a formula to solve for, but we can actually observe that the red and pink region, along with triangle DEF, make up a bigger semicircle, which is this semicircle right here. It's a little bit difficult to see, but this is a separate semicircle. So to find the area of the red and pink region, we would actually subtract the right triangle DEF from that larger semicircle. So we see that the larger semicircle has diameter 17, which would mean it has radius 17 over 2, and the area would be pi r squared. So that's 289 pi over 4. But we're actually looking for the semicircle, so you have to make sure to half that. So the area of semicircle DF is 289 pi over 8. So to find the sum of the areas of the red region and the pink region, we would find 289 pi over 8 minus the area of triangle DEF, which is 60, and we get that by doing 1/2 times 8 times 15. So 289 pi over 8 minus 60 is the area of the red and pink regions. So we actually want to find the area of the shaded regions. So we need to find the areas of semicircles DE and EF and subtract the red and pink region. So the area of semicircle DE is pi r squared divided by 2, and we see that the radius is 4 because it has diameter 8, so that would be 8 pi. And the area of semicircle EF is pi r squared over 2, and the radius is 15 over 2, so that would be 225 pi over 8. So we want to find the sums of the areas of semicircles DE and EF and subtract the pink and red regions. So we would find 8 pi plus 225 pi over 8 minus 289 pi over 8 minus 60. So 8 pi plus 225 pi over 8, if we make a common denominator, that's actually 289 pi over 8. And we are subtracting 289 pi over 8 and adding 60. So that makes our final answer 60. So that was a lot more of a challenging problem just because there were a lot more steps. But the way Pythagorean triples play a role is it helps you at least get started on the problem because you're able to solve for the lengths of the sides. So that was all the problems I had for today. I hope they weren't too difficult or at least that you learned something. Overall, I just recommend knowing your Pythagorean triples so that you can use them and be able to observe any patterns that might occur in upcoming problems. And it's just going to help you a lot in things like countdown round and all sorts of competition math, just because you'll be able to be so much faster and be able to recognize patterns. Thank you for watching.